Welcome guys, I would like to welcome you to my YouTube channel, Learn Physics with IBM, and today I decided again to share with you the results from the practical done by my students. It was 9702 paper 3 October November. I'm solving this paper and I'm just simply sharing the results which my students obtained from their practicals, or one of my students obtained from their practicals, and just to give you a picture of how to present your work in paper 3. So without wasting time, let's go to the question paper. So this is the question paper. So it is 9702 paper 3 October November, advanced practical skills. The paper is supposed to be 2 hours, but since we are answering only the second question, it will be less than 40 minutes, I guess. So let's go straight to the question number 2. I'm recording question number 2 because I spent the whole time making my students comfortable and confident with question number 2 before the next time I go to question number 1. So this was the question we were trying to answer. In this experiment, you'll investigate how the motion of two masses connected by a string passing over a pulley depends on the difference between the two masses. Set up the apparatus with the pulley supported by a clamp. One possible way of doing this is shown. Of course, these are simple apparatus to find in the laboratory. As a teacher, you can print the question paper, you can print the confidential instructions from the teacher's support hub, and then you carry out this experiment with your students. The pulleys are normally found in the laboratory, the masses are normally found in the laboratory. And if you follow the confidential instructions, you'll understand what you need to do to set up the apparatus for the students. So using the masses and hangers provided, make both masses MA of A and MB of B equal to 100. It must be possible to transfer masses from B to A. Adjust the position of the apparatus so that the masses and the pulley overhang the bench. Adjust the height of the apparatus so that the distance h above the bottom of the masses of the mass A and the floor is approximately 1 meter. So don't encourage your students to record this value more than 1 meter. And since they are using a meter ruler, it is going to be in centimeters to 1 decimal place. So I'm using results of one of my students, and she measured. Of course, there's a problem in measuring h. The best thing would have been to clamp the ruler, but they are holding the ruler in their hands. So there's a limitation in measuring h. But my student measured h, and since they said approximately 1 millimeter, it should be very close to 1 millimeter, and she recorded 99.2 centimeters. So discourage your students from recording values not close to 100 centimeters. So it should be either 100.0. Of course, it can't be 100.1. That would be not acceptable. Since you are using a ruler, there is no way you can estimate 100.1. It would mean the student introduced a large uncertainty by measuring more than 100. Then value should be around 99 because it should be approximately 1 meter, which is 100 centimeters. Okay. Then transfer 10 gram mass from B to A. Remember, they were all 100. So if you transfer 10 grams from B to A, it means the mass of A has increased by 10. So MA is 110 grams, and MB has reduced by 10, so it is 90 grams. So when you subtract 110 minus 90, that is automatically 20 grams. There's nothing to be done here. Release mass A from height h as recorded and determine the time t it takes to reach the floor. So every time you take measurements for time, you draw a neat table to show repeated measurements. So my student drew a table. My student drew a table T1 in seconds. She repeated the measurement T2 in seconds. And we were using a stopwatch which measures 2 decimal places. So her first attempt was 2.25 and she repeated and got 2.40. So the average value, she calculated the average 2.25 plus 2.40 divided by 2, and she got 2.325. But because the stopwatch was recording 2 decimal places, she rounded off this to 2.33 in seconds. Of course, that will give you the 2 marks. Then estimate the percentage uncertainty in your value of t. So since she has repeated measurements, she could use a simpler method of absolute uncertainty being half of the range. So she mentioned absolute uncertainty in t is equal to half of the range for repeated measurements which are not the same. So she got this as 2.40 minus 2.25. This is divided by 2. So this is the absolute uncertainty, 2.4 minus 2.25 divided by 2. So she got 0.075. That is the absolute uncertainty in seconds. So then the percentage uncertainty in t is actually 0.075 divided by the actual value of time, which is 2.33. Then multiply this by 100. So that is divided by 2.33, then times 100. So she gets 3.22%. So this is 3.22%. I'm very certain she would get those 2 marks. But of course, I told you in one of the videos that if you measure in measuring time, you expect a reaction time of approximately 0.2 in starting and another one of 0.2 in stopping. So there's a reaction time of about 0.4 in just starting and stopping. So in a stopwatch, you can use the absolute uncertainty to be between 0.2 up to around 0.5 seconds as the absolute. You just choose the one value from this, then divide it by the true value times 100 to get the percentage uncertainty. Of course, I don't expect the answers to be the same with the half of the range, but the examiner is interested in the method, not the answer. So here, the method I used is half of the range, or you could choose a value in that range between 0.2 to 0.5 to be the absolute. For example, I can say 0.3. So I'll tell the examiner that the absolute uncertainty is 0.3 seconds. Then I calculate the percentage uncertainty in t as 0.3 divided by my true value, which is 2.33, then times 100. This will be another method. Then transfer another 100 grams from B to A. So again, we have transferred another one from B to A. So A has now become 120 grams. Then B has reduced by another 10, so it becomes 80 grams. So when you subtract, I think that is 40 grams. Then she repeated find the value of T. So she had to do another table because she has to repeat a measurement. Okay, so she repeated. So she got T1 in seconds, T2 in seconds. So since the mass has changed, the value of time is most likely going to change. So she has here 1.28. Then the second attempt she has 1.34. Then she obtains the average 1.28 plus 1.34 divided by 2. So she gets 1.31 and records 1.31 seconds. Okay, I'm very sure this would give her all these 3 marks. Even it is suggested that the relationship between MA, MB, and T is that where K is a constant, using your data, calculate 2 values of K. So I encourage my students to begin by making k the subject. So she made k the subject as being equal to t squared into ma minus mb. So she got the first value of k, calling it k1, using the first values where t was 2.33. So this is 2.33 squared times ma minus mb. The first value of ma minus mb was 20. So she said times 20 without changing the units. Then k2, the value of times 1.31 squared times ma minus mb, which is 40, without changing the units. Of course, if we wanted the units, k1 would be s second squared times g. It will be second squared times g, but units are not required here. So she pressed her calculator, 2.33 squared times 20, and she has the first value of k is 108. 108 point. She recorded 108.6. And then the second value of k, 1.31 squared times 40. So she has 68.6. Then the question which asks to justify the number of significant figures, she just had to mention the number of significant figures are given here. So ma minus mb, of course this 20 is not as a result of rounding off, then we can consider it to be two significant figures. And 2.33, the 0 here is not as a result of rounding off, so it can be considered a significant figure. So she mentioned that since t squared is, or since t squared is to 3 significant figures, and ma minus mb is to 2 significant figures. So to maintain accuracy, k should be to at least 2 significant figures. So it means you could write k to 2 significant figures or more, because the smallest number of significant figures in the raw data is 2. So that is how we answer that question, and I'm very sure the student will get that mark. Explain whether your results support the suggested relationship. So here I told my students to start by stating a criterion, and my student said let my percentage acceptance range of error in k values. Of course, you're not supposed to write it there. Let my percentage acceptance range of error in k values be, she said, 15%. Then she calculated the percentage difference in k values. percentage difference in K values, where she got 108.6 minus 68.6, 108.6 minus 68.6, then she divided by the highest, which is 108.6, then multiply this by 100. So 108.6 minus 68.6 divided by 108.6, then times 100, where she got 36.8%. This is quite big. So she just made a conclusion and said, since percentage difference in K values is greater than 15%, K cannot be considered constant. K cannot be considered constant, and the relationship is not supported. So since the percentage difference in K value is greater than 15%, we cannot consider K to be constant, so the relationship is not supported. Then some of the limitations, uncertainties or limitations that I expected included the following. My students normally write the first one as it is almost the same for almost every practical, unless in some practicals they are asked, or you're asked to calculate three values of C of a constant. So in that case they would say 3, but since there are 2, they would say 2 readings are not enough to draw a valid conclusion. To draw a valid conclusion, 2 readings are not enough to draw a valid conclusion. So this could be solved by taking more readings and plotting a graph. So take more readings and plot a graph. Or you would take more readings obtain more K values and compare them. Then the second one, I expect friction and the pulleys. So friction are the pulleys because they are not lubricated. So I expect friction at the pulley. Friction at the pulley, of course, that one is easy to solve. Lubricate the pulley. You add grease or oil, lubricate the pulley. They could lubricate the pulley. Then the other one I expected is the stand was shaking. My student told me the stand was shaking, or the stand was moving as the mass is moving, as the masses are moving. So the stand moves. That one is easy to solve. If the stand was moving, you just fix the stand on the table using a G-clamp or add weights to the base. So fix the stand on table with a G clamp, or simply add weights to the base. Add weights to the base. So you could add weights to the base of the stand to prevent it from moving. Then the other one I expected from this was that the mass values were not very accurate, because they were just combined, so the mass values may not have been very accurate. The mass values not accurate. The mass values could not be accurate because we did not measure them even though they were labeled. So here you just use a balance to measure the actual mass. Use the balance to measure the actual mass. Okay, then the other one could be the one I expected. It was difficult to judge the starting point. One student told me the masses hit each other. Okay, I will start with this one. The masses hit each other, or the masses were slipping off the hanger. Masses hit each other. I observed that myself. For some students, the masses were slipping off the hanger. The masses slip off the hanger. So this one was easy to solve if we wanted to solve it. If the masses hit each other, you would use a larger pulley so that there is a large distance between the masses. For the masses slipping off the hanger, you could fix the masses with tape. So use a larger pulley. If we had used a larger pulley, there would be a big distance between the two masses. They wouldn't hit each other. If we had fixed the masses with the tape onto the mass hangers, they wouldn't actually fall off or slip off. So fix the mass with the tape. Okay, then also it was difficult to judge the starting point of releasing the masses. Difficult to judge. Difficult to judge the starting position. Difficult to judge the starting position. And that could be solved by simply clamping the ruler close to the masses. Or we could use an electromagnet to release the masses. So clamp the rule close to the masses. You would use an electromagnet to release the masses. So that means you would fix the electromagnet at one position and every time release the masses from that position. Also, I noticed that it was difficult to measure the time as it was too short. In fact, the reaction time could have been larger compared with the time we measured. So difficult to measure the time as the time is too short. Or you would simply say reaction time was larger. Reaction time larger compared with the time we measured. So that one would be very easy to solve. If the reaction time is larger, it's only because the masses were falling through a smaller distance. So you could improve this by making them fall through a greater height. So you could say drop masses through a greater height. Alternatively, we would use light gauge to measure that time. Use light gauges with a timer. Alternatively, we would use a motion sensor. Of course, the motion sensor would be placed below the masses. Use motion sensor with a data logger. Of course, the data logger will be helping in measuring the time with a data logger. Alternatively, for such small values of time, you could use a video camera with a timer. Use a video camera with a timer. So you would use a video camera with a timer to record the experiment and then view frame by frame. Use a video camera with a timer and view frame by frame. Okay. Yeah, so that is the practical which my students did, and I hope you have picked something from this experiment. You can try it out and try to follow their solutions and compare with your results. You may not get exactly the same results like my students, but this is just to give you a picture of how to present your practical report. Until next time, bye bye.